Yesterday we discussed single stage negative feedback wideband structures. Basically that do not need any frequency compensation, hence the negative feedback results in wider bandwidth than otherwise. Therefore, this is a common collector stage which is essentially a voltage controlled voltage source with unity gain, normally used as a buffer stage, which is a wideband structure because of its complete negative feedback, voltage feedback. This is a common base stage, which is a current controlled current source. The common emitter output current is totally fed back to the base, then it results in common base structure with total current feedback, and therefore, I naught over I I becomes equal to 1. So, it can be used as a current buffer just as we use this for a voltage buffer. So, this is a wideband structure. Again here we have Z feedback, this is Y feedback. So, this is a voltage controlled current source, current controlled voltage source. Correspondingly, the transfer parameters are written here. I naught is V I by R E, V naught is equal to minus I I R F. All these are wideband structures, and a combination of these okay, also results in wideband structures, because if I want a voltage controlled voltage source, I will combine this with this just as we did yesterday and built up an IC. If I want a current controlled current source, I combine this with this, I put this first and next. So, I can therefore build up wideband structure by combining any one of these suitably. We have therefore negative feedback structures with two transistors. Two common emitters cascaded together. What are the negative feedback wideband structures? Now, the moment you have two transistors, you have three time constants like input, intermediate, output, and therefore, it is likely to go into oscillations because of the three time constants, and therefore, it will need compensation. Whereas, these do not need any compensation, and they retain their wideband structure even while cascading. Here this needs compensation, and therefore, the compensation that we adopt here is essentially pole zero compensation, which we have discussed. So, the negative feedback structure also we have discussed earlier. If it is H feedback, it is this structure. If it is H feedback, results in a wideband amplifier with gain equal to 1 plus R2 over R1, a voltage controlled voltage source wideband, and therefore, we can split this R2 in a suitable manner, R2 dash and R2 double dash, and put a capacitor across one of those, so that we can adopt our pole zero compensation in order to prevent the oscillation. So, this is what is done in the case of wideband amplifier design. We will split this as let us say R2 dash and R2 double dash, and provide a suitable capacitor across this, so that frequency compensation can be done. Most of the time it is very difficult to find out exactly where these poles are located, and therefore, you can in any case split this and put a capacitor, keep varying it until it stops oscillating, and then provide a little bit more, so that there is enough margin, so that at all conditions it is not going to oscillate. And therefore, this kind of compensation results in the widest bandwidth for the amplifier, which is a voltage controlled voltage source. Similarly, if it is the same structure, you can make it a current controlled current source by G feedback. This also we have discussed earlier while discussing feedback. This will result in a current controlled current source of the same gain 1 plus R 2 over R 1, and therefore, this also is a wideband amplifier. Again, this might also need the same type of frequency compensation that is given in this case for making it work. Beyond this 2 stages, normally that means connecting 3 amplifier stages, it is very difficult to make it go work suitably as a wideband negative feedback structure, because invariably the oscillations persist. It is very difficult, because the number of time constants increase to 4, minimum 4. So, it is enough if we discuss all these amplifiers, which we have already done, as wideband structures. So, these wideband ICs are also available in the market as video amplifiers. So, this much about video or wideband amplifier should be sufficient for us to be conversant with how to design such amplifiers, what kind of frequency compensation we should provide, etc. We have been discussing some special type of amplifiers so far, which we call as wideband amplifiers or video amplifiers. In fact, whatever we have discussed in terms of bipolar structures become valid also for the field effect transistors, same structures. Okay. Instead of common collector, it will be common drain, right, and common base, common gate, like that, and the feedback structures as well. So, we will go to another special type of amplifier now. This is called power amplifier. Essentially, all amplifiers we have learned are power amplifiers, but what we discussed earlier are the ones which are normally designed at the input of a system or pre-amplifier stages, or maybe the intermediate amplifier stage, or they are basically small signal amplifiers. Where essentially the power gain is very high, infinity basically, and the efficiency has never been considered while designing such amplifiers. What is efficiency? After all, you feed some input power and you get power gain, huge value of power gain. How do you get this gain? The signal has low power input at the input stage of the amplifier, and output it has been amplified considerably. This power comes from the DC bias. The DC power that is necessary to bias the active device is getting converted into the useful signal power. Now, how much of this biasing is to be provided so that the signal power gets converted into useful power, output power, that depends upon your design basically. We are not bothered about that initially simply because of the fact that since it is small signal, the biasing currents etc. are so small that it is of no consequence. Finally, when it comes to driving a loudspeaker whose impedance level may be, resistance level may be of the order of few ohms, okay, and we want watts of power, then we are now going to think of how much power we should input to the amplifier in order to get what power we require, let us say 10 watts or 20 watts. And therefore, efficiency comes into picture when we deal with final stages of amplifiers. So, these are pre-amplifiers here. These are small signal amplifiers, efficiency no consideration. But in a power amplifier where we are dealing with considerable amount of output power, of the order of maybe watts or sometimes if these are transmitters and all that kilowatts. Okay. So, efficiency definitely will come into picture, how much power we have to input in order to get this much of signal power. So, watts and kilowatts of power, right. So, what are these amplifiers that we have already discussed? Let us consider a power amplifier, its characteristics. Let us consider a common collector stage, because this is basically a good voltage controlled voltage source, can also act as a buffer stage. Since our load is going to be, I said, maybe a speaker or something like that, and therefore, the load is going to be of the order of few ohms. We do not want our previous stage to be straight away loaded by these few ohms. So, we put a buffer stage here. So, the load is going to be RL here. This is VCC, let us say, this is grounded, and the output here, if this is Vi, the output here V naught is going to be very nearly equal to Vi. This is sinusoidal varying, this also will vary sinusoidally. The gain of this is very nearly equal to 1. This is a commonly used power amplifier stage. The input power is small because the input current is of the order of beta plus 1 less than the output current. This is the output current. So, input power is going to be much less than the output power, that is definitely true. And what is going to be the output power, what is efficiency, etc., we will try to understand in terms of this. Apart from this efficiency part, power gain is an important thing, efficiency. The other thing of importance in power amplifier is, in fact this is important in all amplifiers, but in power amplifiers this is all the more important because the load is going to be pretty small. If it is a voltage amplifier, the load is going to be pretty small. So, distortion is significant, particularly because the signal levels are high, whether it is voltage or current, and we cannot consider the amplifier as a small signal amplifier at all. We cannot do the analysis of this kind of thing that we have done in the previous stages, replace the thing by a small signal equivalent. It is not, because the signal is varying considerably, and therefore, in power amplifier analysis it is futile to discuss about distortion without considering the nonlinear aspects of the device. So, the nonlinear aspect of the device comes into picture. If it is a feedback structure, the nonlinearity is automatically reduced. Here V naught is equal to V I is valid for large signal also. So, that is why we have chosen for an illustration a structure which is basically having low distortion. We have to find out the efficiency and power gain of this structure. Now, we say that in order to make this operate for signal which is going both positive and negative AC signal, we have to operate it at a quiescent point. So, we know that this is having some I quiescent. Obviously, we have V B quiescent here in order to make this operate at I quiescent. So, V B quiescent minus V gamma, this one, divided by R L in this case is I quiescent. Please understand this, this is the DC voltage. In order to make this work at I quiescent, I have to apply this much DC voltage V B quiescent minus V gamma divided by R L will be very nearly equal to. There is no point in considering alpha etc. in this case, because alpha will consider as unity. So, this is the quiescent current in this. Therefore, even when there is no signal applied, this is dissipating power. What is the power dissipated in the whole of the structure? It is nothing but VCC into IQ. This is the power input. So, we will call it PI. So, the power input. This current being beta times less, okay, the biasing circuits etc., if they are needed here, for example, how do you get VBQ? You can put maybe a resistance arrangement here. This we have already discussed earlier. Thevenin's voltage you can generate by putting R1 here and R2 here and making R1 by R1 plus R2 times VCC equal to VBQ. This we have discussed earlier. So, this is the biasing arrangement for this power stage. What I am trying to say is the total current is IQ plus the current drawn from here, which is VCC divided by R1 plus R2. So, actual power input is not only this plus VCC, okay, into VCC by R1 plus R2. This is in fact the total power dissipated in this whole so called power amplifier stage. This is required for biasing the transistor. This is going to be pretty low. By selecting R1 plus R2 large, not too large, because this current VCC by R1 plus R2, this should be definitely much greater than the base current. We have ignored that base current. That means, this current VCC by R1 plus R2 should be definitely greater than IQ divided by beta. this is let us say beta minimum worst case. So, you have to select R 1 plus R 2 larger than this condition, and it should be obviously less than VCC by R 1 plus R 2 should be much greater than or much less than IQ. This is the way you have to select, because IQ is anyway necessary to bias this transistor, okay, and IQ must be greater, much greater than VCC by R 1 plus R 2. If you select all that, then we can say that input power is essentially, okay, VCC into IQ, approximately. This is an illustration of how any power stage has to be designed. If the power transistor is operating at IQ, rest of the current that is drawn for biasing purposes should be much less than that current, okay, and the corresponding resistance etc. are chosen in that manner. So, this gives an idea as to how this power stage is now designed. This aspect of deciding about all these currents were of trivial nature when we were designing this so called small signal amplifier. We never bothered about that, and we never bothered about the power input at all. That was because the IQ was very small compared to what was necessary in the case of a power stage, which is the final stage. Now, if it is having IQ flowing through this, what is the signal swing here? IQ, I am applying a Vi here, and V naught is very nearly equal to Vi. Let us say Vi is a sine wave. What is the maximum value of V naught you can have? I will vary here as IQ plus or minus I. Because of the signal, this signal current will be superimposed over the quiescent. So, delta I can be made equal to minus IQ, that we had discussed earlier also. So, that the total current becomes equal to 0 on one side. So, on one side the current can go down to 0, the instantaneous value of current can go down to 0, because as signal is applied, this current is going to be, instantaneous current is going to be increasing or decreasing here. So, this is going to be either equal to 0, or on the other side it can keep on increasing, there is no limit actually. As long as Vi keeps on increasing, this current can keep on increasing without any limit. Now, what is the maximum current ultimately it will lead to, where Vi becomes maybe almost up to VCC, because this might be coming from the previous stage, and previous stage is also connected to a supply like VCC, and therefore, the maximum voltage you can have there is at most equal to peak voltage is VCC. So, this can go, this base voltage can go up to VCC. If the base voltage goes up to VCC, this voltage can go up to VCC minus V gamma, okay. And therefore, V naught, the highest value of V naught can be VCC minus V gamma. If VCC is large compared to V gamma, if VCC is very large compared to V gamma, this is VCC itself. So, we can have the V naught peak equal to VCC minus V gamma, which is very nearly equal to VCC, and I maximum corresponds to actually I peak we will put it, I peak corresponds to I q itself. Therefore, current swing on one side, current swing is the one that limits, on the other side voltage swing is the one that limits. So, if we want now equal swing on either side of the quiescent, let us see if it is a sinusoid, the quiescent is here V naught q, and on this side it can go almost up to V p, actually it is V p minus V gamma. On the other side it can go up to 0 when the instantaneous value of current through the load becomes equal to 0, instantaneous value of voltage also is 0. Okay. So, it goes from 0 all the way up to V p. So, if it is to be symmetric, obviously V naught q has to be equal to V p divided by 2. It is to be symmetric, this is V p by 2 and that is V p by 2. So, if this is V naught q is V p by 2 and I q R L is equal to that, so I quiescent is already fixed for the best operation as V p divided by 2 R L, V p by 2 divided by R L. So, that this is because I q into R L is now V p by 2. So, quiescent current is V p by 2 R L or V p is equal to V c c, okay, divided by 2 R L. So, we said V p is very nearly equal to V c c under the best situation. So, V c c by 2 R L. So, if let us say supply voltage is 10 volts and R L is let us say 100 ohms, 10 volts 100 ohms, then this will current will be 10 volts divided by 200 ohms. So, let us say if V c c is 10 volts, okay, R L is 100 ohms, then I q is going to be 10 by 200 ohms, okay, which is 0.05 amperes or 50 milliamperes. Now, you can see the kind of operating current I should have just for this load of 100 ohms with supply voltage of 10 volts in order to have symmetric swing going up to all the way up to half the value, that is 5 volts. I have to have operating current of 50 milliamperes. So, if 50 milliamperes is the current, then what is the power input? Power input is going to be 50 milliamperes, okay, into 10 volts. So, that is going to be 500 milliwatts or 0.5 watts. This 0.5 watt of power is continuously wasted. Suppose you are using a battery there, even when the signal is not coming, this power is being wasted. So, this is why it is inefficient. In order to keep it in readiness for a swing which is going to be coming maybe some time or other, we are not sure whether this much swing is going to occur at any time. We are now wasting 500 milliwatts of power just waiting for the signal to come. So, please, this is what is called as class A operation. This kind of operation where in order to receive, let us say, king, you are receiving the king, you do not know when the king is going to arrive. So, in order to prepare him, okay, in order to prepare yourself to receive him, you are continuously wasting certain amount of money, right. All the welcoming party, the band, the decoration, all of them have to keep waiting, and they are going to spend only few minutes maybe just playing their band when the king arrives. But since the time is not known to you, right, maybe you have to wait for 24 hours or 48 hours, who knows. So, this is what is called as class A operation. This is an inefficient way of operating. What is the best way? We can say the king is coming, but the time is not known. But the moment the king comes, we will be woken up, right. So, the bandwalas and the reception committee, all of them are given a chance to sleep, right. The moment the king comes, right, they will wake up and then start playing the band. That is really what is called as class B operation. That you will be sleeping, and only when the signal comes, okay, you are getting ready. So, class A operation is an inefficient way of power amplification. Now, let us see what is the efficiency. Under the best condition, what the efficiency is. The signal has to be, for the efficiency to be maximum, signal has to go up to VCC, right, because maximum power has to be dissipated in the load. What is the power dissipated in the load? Let us discuss this. If it is a symmetric swing and the voltage is Vp sin omega t, the current is going to be, this is the voltage across the load, and the current is going to be Vp divided by RL sin omega t. This is the current, that is the voltage. Then the power dissipated in this is going to be Vp divided by root 2 RMS value and Vp by RL divided by root 2. So, Vp squared divided by 2 RL. Vp divided by root 2, Vp divided by root 2 into Vp by RL by root 2, which is Vp squared by 2 RL is the power output. At any time, if there is sine wave inputted, output is going to be a sine wave, and therefore, at any time the power outputted is Vp squared by 2 RL. What is the maximum power outputted? When Vp becomes equal to Vcc, the peak value. Why should we take the maximum power? We know that the power dissipated in the transistor, okay, that is power dissipated in the transistor as well as the resistor, rest of the circuit, okay, power wasted, let us say, is nothing but power inputted minus output power. What is the power inputted? Let us see. Power inputted is going to be Vcc, that is the DC, okay, into IQ, because AC is not going to cause any power, right. The IQ. IQ is already decided as, okay, Vcc divided by 2 RL. This we have already decided, Vcc divided by 2 RL. Okay. So, this is going to be Vcc squared divided by 2 RL, and output power is Vp squared divided by, okay, 2. And what is the value of Vp? V p at which you get maximum output power is going to be V c c divided by 2. On one side it can go up to V c c by 2, on the other side it can go up to V c c by 2. So, power wasted is minimum only when this is maximum, otherwise let us say power wasted is fully the power inputted when the signal is not there. The entire thing is wasted in this circuit as DC power. Now, this DC power gets converted into some amount of useful power, and the amount of useful power is maximum when V p is equal to V c c by 2. So, this becomes V c c squared by 4 8 R. So, power output is maximum when V p is equal to V c c by 2. On one side it can go, if this is V c c by 2, on one side it can go up to V c c, on the other side it can go up to 0. So, it is V c c by 2, and therefore, that much power is wasted in the circuit. Efficiency is defined as, this is efficiency. Power outputted divided by power input. This is going to be the maximum efficiency. If you say eta max, you have to consider the maximum output. Input is constant, V c c squared by 2 R L. So, actually speaking, generally this is V p squared divided by 2 R L, V p squared divided by 2 R L divided by V c c squared divided by 2 R L, or this is V p by V c c whole square generally. And since the maximum value of this occurs when V p is V c c by 2, the efficiency is only, maximum efficiency is only how much? 25%. So, let us understand this very clearly. Maximum efficiency of this class A stage as given here is 25%. Such is the case of any class A stage. I have used for demonstration only common collector stage. Even if you use common emitter stage with load here, such is the case, right. So, it is of no difference what kind of stage I use, whether it is FET or bipolar, as long as it is class A, the maximum efficiency of such a stage is always going to be less than 25%, because this is only the best efficiency possible, and it is not possible for us to have the signal always at V p. It is going to change, signal is going to keep changing depending upon your output. So, this is maybe an audio signal. So, it at best it can reach V p at a certain given moment, that is all. So, this is always less than 25%. What does it mean? If I want this 25%, that is this power V c c squared by 8 R L to be V c c squared by 8 R L to be, this is the useful power, let us say 1 watt. then VCC square by RL VCC squared by 2 RL is going to be 4 watts. That means, the quiescent power I must be prepared to waste is 4 watts in order to get a power of 1 watt output. This 4 watt is going to be dissipated continuously. When signal comes, and that also when it reaches its peak value, then only you are able to get an 1 watt output, and then 3 watts is the output dissipated in the stage. So, you can therefore imagine the amount of heat sinking and all that thing that is required for the device or the circuit itself. This 4 watt is to be dissipated in the circuit. Okay. How much is going to be dissipated in the resistance? How much is going to be dissipated in this? That is, half is going to be dissipated in the resistance, half is going to be dissipated in the transistor. If 4 watts is the quiescent power, and this is VCC by 2. So, VCC by 2 square divided by RL is dissipated here, and the rest of it is dissipated here. So, 2 watts will be dissipated here and 2 watts will be dissipated here. Under the signal situation, it will dissipate less, because some of the power is converted into this thing. So, the transistor that you have to use for delivering 1 watt should be 2 watts, but the circuit actually is going to dissipate 4 watts under quiescent situation, because that is a DC power that is going to be dissipated here. So, this DC current is flowing in addition to the AC current. There will be some amount of DC power continue to be dissipated, even when the AC is there. So, this particular transistor and this resistor, both of these things are dissipating maximum amount of power when the signal is not there. When the signal is there, some amount of that power is getting converted into signal power, useful power, AC power. Now, for this example of VCC is equal to 10 volts and RL equal to 100 ohms, you have seen that 50 milliamperes is the current, and we can also find out what the power inputted is 500 milliwatts. That means, from this you can only get 1/4 of this power as signal power. That means, output power could be, under the best situation, 1/4 of 500 milliwatts. Is this clear? Similarly, if you have to design for a specific output power, you can find out what should be the quiescent input power, and based on that you will select the transistor and the load. Load is normally given to you, it may be a speaker. So, you will select the corresponding transistor based on this. What are the other factors which are important? In power stage, apart from this power that is to be dissipated in the active device, the current is also important, and the voltage. The maximum current is the peak current when this voltage goes to Vp, that is VCC itself. So, the maximum current in this circuit I max is going to be V peak divided by RL, which is VCC, right. In fact, instantaneous value of V peak, right. So, V naught peak. So, that is VCC itself. So, VCC divided by RL. This is the point at which maximum current, load current is going to flow. The instantaneous value of voltage is VCC. that divided by RL is the maximum current. That current has to flow through the transistor as well. So, your transistor rating should be better than VCC by RL. This is the maximum current. And the maximum voltage across the transistor is VCC itself, when this voltage goes down to 0, right. So, maximum voltage and maximum power is going to be determined by, this is VCC squared divided by 2 RL, that is the input power. Half of it is going to be VCC squared divided by 4 RL. Okay. That is the maximum power to be dissipated in the transistor. Okay. When the voltage here increases, the current decreases. When the voltage decreases, current increases. So, the maximum power under the quiescent situation is VCC squared divided by 4 RL. Therefore, for the transistor this is, right. So, the active device, it is VCC squared divided by 4 RL. So, based on all these factors, you will select the transistor that is necessary for this. Let us now summarize what we have learned so far. In class A power amplifier, given a supply voltage of VCC and load of RL, we have connected a transistor in series with this, so that we can control the power in RL, or we can get the output power in RL. So, Pi is equal to always VCC into quiescent current in this. Pd at that point of time when signal is not applied gets dissipated in the transistor and the load. So, Pd in general is nothing but VCE, voltage across the transistor, into current through the transistor, VCE into IQ. Pd through the load is VCC minus VCE into IQ. For maximum output swing, on the other hand, VCE we wanted to make it equal to VCC divided by 2. Then IQ becomes equal to VCC by 2 RL. Okay. And another situation, Pd is going to be VCC squared by 4 RL in both load and transistor. This is a DC power dissipated both in the load and the transistor. Ultimately, therefore, Pi is sum of these two powers, which is supply voltage into quiescent current, and that is VCC squared by 2 RL. Half of it gets dissipated here in the transistor, half gets dissipated in the load. Then under signal input situation, V naught is Vp sin omega t, I naught is Vp by RL sin omega t, and P naught is Vp squared by 2 RL. Under this, I naught q continues to flow, DC current continues to flow, and DC dissipation in the resist load continues to be the same. So, this dissipation remains the same. Sum of the transistor active device dissipation, on the other hand, gets converted into useful signal power. So, transistor dissipates less power during active cycle, and that power is given out in the load as the useful power. That is how the active device is responsible to convert its DC power into signal power. So, if let us say we have the input power equal to 100 watts, initially 50 watts will be dissipated by this and 50 watts will be dissipated by this, and the maximum signal output power you can get when you have 100 watts is 25 watts. Okay. At that time 75 watts is going to be still dissipated in the circuit, goes waste, out of which actually earlier 50 watts was getting dissipated here, and that 50 watts continues to be dissipated, then this is going to dissipate further DC power of 25 watts. this 25 watts which was earlier getting dissipated as DC power is getting converted into AC power. So, that is why this active device is responsible for converting the DC power into AC power.